Okay, hi everybody. Today we want to talk to you about how GPS was created, how it works, and how it may be used in the future. My name is Marlene.
I'm Charlie.
I'm Daniel.
And I'm Gagan.
So a little bit about the history of GPS. We know that GPS was invented during the Sputnik era when scientists first experimented with the technology to track the Sputnik satellite. They accomplished this by varying radio signals and observing what became known as the Doppler effect. The Doppler effect is either an increase or decrease in the frequency of a wave produced by a moving source with respect to an observer. The US military also started using the technology during the mid-1960s to track weaponry. Navy submarines, for example, were able to observe satellite changes in Doppler and figure out the location of a submarine. In modern times, GPS is a big part of our lives. The government uses the precise positioning system for national defense, scientific needs, commercial needs, etc. And as civilians, we use the standard positioning system to help us figure out where we are located. The PPS and SPS are different levels of GPS, and as civilians, we are restricted to using the SPS, unlike the military. GPS, however, was not always as reliable as it is today. GPS became widely available to civilians in 1999 through a cell phone called the Benefon Escape. It was made by a company called Benefon, and you can see a picture of this phone on the screen. This led to many advancements, though, including the GPS feature in cars that we see today. In 2000, the government approved the use of more GPS signals to increase its accuracy for civilians.
How GPS or the global positioning system operates is that it operates on the basis of trilateration to calculate the position of a person. Trilateration calculates the position of the person by finding the distance the person is from three different orbiting GPS satellites within line of sight. It finds these distances by analyzing the signals each GPS satellite sends to the person's receiver, or each signal is timestamped to to the time when that satellite sent out that signal based on that satellite's atomic clock. So the person's receiver would then analyze that timestamp and would then analyze the time it received that signal and would then take the time difference between the two and multiply it by the known value of the speed of light to calculate the distance that that satellite is from that person. It would do this for all three satellites. It would find all three distances, and then these distances would then be used to create three circles, each circle for a satellite, where the satellite would be at the center, and each radius of that circle would be the distance from that satellite to that person. The next part would be to locate the intersection point of all three circles. And since we have three circles, this would occur only once. And this intersection point would be the exact position of a person. Now, realistically, GPS operates in a 3D manner rather than a 2D manner. So trilateration would operate with spheres rather than circles. And while trilateration requires three different orbiting GPS satellites to function, a fourth satellite would be inserted into the whole process to increase the overall accuracy of the entire process. Can you go to the next slide? For applications, GPS can be operated by numerous receivers with each having its own different purpose. A most common application would be from mobile telephones, providing users with their real-time position and the ability to accurately travel to other locations. Another example could be in the aircraft industry, where receivers are providing real-time aircraft position to pilots and ground control, increasing the overall safety of that industry by allowing us to monitor who is in the air or who isn't. Another example could be farmers equipping GPS receivers onto their equipment to map out plantations, to map out which crops to harvest, which not to, and to allow them to still work on their fields when visibility can be poor. There are a whole list of applications, of GPS applications, but this just gives us a brief overview over some of the applications there are.
In November 1995, an experiment called the GPS Attitude Determination and Control System, or GADACS, was set to fly as part of the Spartan spacecraft. This experiment aimed to provide two important results to the aerospace community. The first being that the GPS sensor data would be compared to onboard high precision gyroscopes and a star tracker, and error analysis would result in the first spacecraft mission to quantify the accuracy of GPS attitude solutions. The second result of this experiment would be to control the spacecraft using the GPS attitude sensor exclusively. And during this control portion, based off of the GPS attitude data, the controller was to hold the spacecraft fixed inertially in a 2-degree dead zone by correcting for gravity gradient as well as aerodynamic and magnetic environmental torques. And as you can see on the figure on the right, this is the configuration of the Spartan spacecraft in which the GADACS experiment was performed. Next, please. Okay, so the figure on the left shows or displays the system response to a large 20-degree initial error in the roll axis. As shown, the system captures the roll error to within this 2-degree dead zone that was required within 250 seconds. This displays that the system can successfully correct for environmental torques and attitude error based off of the GPS data alone. And while traditionally thought of as a navigation system, the GADACS experiment demonstrated GPS to be a formidable sensor for attitude determination as well. And it gave accuracies up to 0.1 degrees or less. Next.
So in addition to being able to locate people and devices on Earth, GPS can also locate nearby satellites. The primary method of doing this is by using the SNR, or signal to noise ratio. And the SNR is really a simple and effective way to get a ballpark where a neighboring satellite can be. The method is based on using the bore site of the GPS satellite. As you can see on the figure to the right, the unit vector B denotes this bore site. Typically, neighboring satellites will emit a signal which can be caught by the GPS dish and reflected back into the antenna. That signal strength relies on the angle between the satellite and the GPS bore site. As that satellite radius gets closer to being perpendicular to that bore site vector, that noise is going to increase and the signal is going to drop off. That means that physically the GPS is going to pick up more noise and a signal than if the target was either collinear with the bore site or close to collinear. However, the signal to noise ratio gives us an idea of where that satellite could be. So the crux of this method is really based on a valid SNR to alpha map, where alpha denotes the angle between the satellite vector and the bore site vector. These maps are really developed on the ground with a lot of testing, and any patches can be uplinked to the satellite to correct for any error. So we can go to the next slide. So here's a couple sample SNR to alpha maps. As you can see, as the SNR increases, the alpha decreases. In other words, as signal strength increases, the target satellite is more in line with that bore site vector. This was tested on multiple GPS satellites targeting multiple different targets, and they all had the same trend. To quickly summarize SNR attitude determination, as the SNR increases, this means the noise decreases, which implies the satellite is more in line with the GPS antenna, giving us the direction of where that satellite is. On the other hand, with a greater alpha, more noise is generated when reflecting and transmitting into the antenna. We should therefore expect a lower SNR, which we can see in the sample maps above. Go to the next slide. So GPS really has a bright future ahead. The greatest thing that we can do is to increase the GPS swarm and load it with more powerful technology. With more GPS satellites, we can achieve greater coverage and more accurate positioning. We've also started to use atomic clocks as opposed to digital clock signals. This allows GPS satellites to maintain the same time and remain synchronized and not succumb to relativistic effects over time. Greater power technology is also being loaded into these GPS satellites. With greater power, a GPS can offer much more accurate positioning in dense areas with lots of E&M noise, such as big cities. A more tangible effect of the future GPS is the advent of autonomous driving. For the same reason, GPS benefits the average consumer due to better technology, such as more coverage and better synchronization. Autonomous mobiles and their networks will also be able to use this better data to get a better sense of the roads to allow for a safer, more advanced self-driving future. Go to the next slide. So to quickly summarize what GPS is and what it does, GPS originated in the Sputnik era as a means for US Navy military navigation. And as all military technology does at some point, the technology was made available for consumer use. It was quickly popularized in mobile phones and automobiles as a means for positioning and navigation. The technology works via trilateration, which basically is taking 3 GPS satellites that are required to see an object, and the intersection point of the resulting 3 circles bound by their radius gives an exact location of where that object may be. GPS is used all over the world in several different sectors, such as in aircraft, emergency services, consumer navigation, farming, etc. And it's one of the main ways we can visualize roads and get positioning and navigation for objects. But it's not just a consumer tool. GPS can also be used to measure where a nearby satellite is in space. And by using an on-the-ground tested map that correlates signal strength to how low a satellite is compared to the GPS, a GPS satellite is able to show the location of neighboring spacecraft and downlink this information to the ground. The future of GPS mainly lies in greater numbers and the greater technology that we can send with it into space. With more GPS satellites, we'll get better coverage and better accuracy. With better timing solutions, we can maintain synchronization and be more immune to relativistic effects. With greater power output, GPS satellites can offer better positioning and navigation in densely populated areas and big cities where there's a lot of E&M noise. And with all of these advancements, GPS can lead to a lot of different things, such as a self-driving car future. So with all this additional and more accurate data, GPS satellites offer tons of more use to the world, both to consumers and to the industry. Thank you.
Thanks for watching, guys.